It's only Steve. Who else would do that?
Really? Okay. Okay, you don't need to close it. Yeah, so from the receiver, I said that that stage of the receiver is called the intermediate stage.
Yeah.
From here we have the final stage. So this ends the receiver. This ends the receiver. And from here, what I will just talk about is that from here the signal splits into two polarizations. The right circular polarization and then the left circular polarization, which is called LCP, RCP. And from there, that signal gets into the root port for it to be digitized. So from all this point, the signal is still analog, then it needs to be digitized in the root. So let's use the final rack and I explain that when we come to it. Yeah, so from here, who's going there? Who's going behind me? Yeah? Oh, please don't go through. I'm not through this. Okay, so from here, the
Guys,
signal
did you
gets...
say don't go through the
Don't go
come
through
there,
there,
come
so
there.
He wants to see what's there.
No,
Come
please.
there.
We have a lot of cables dangling there. One cable you pull out will cost us 2 hours to fix that. Okay, so from here we come to the root board. The root board is FPGA. If you've done electronics, you should know what this means. At least most physics students should know what this means. FPGA. Okay, FPGA is Field Programmable Gate Array. Yeah.
I was waiting for you to say.
Yeah. Actually, that's why how all students are. They say, "Oh, I don't know. I was just about to say." Yeah. So it's made by the Casper Group. If you into astronomy, you will hear this term, Casper. Go find out who they are.
How do you spell?
CASPER. Okay. So that's it. So from here, the signal gets digitized. So the analog signal will get digitized, and then they can then be recorded as digital signals on the analysis computers. From here, this signal here works with this machine, which is called the reader, and then just for illustration purposes, written the analysis computer. So from here, we can see the signal now, and whether it's a spike, whether it's a flat, or the power of it and all that. Then when you record it, you should know what you should expect. Okay. From here, there are two modes of operation here. For the roach, that means the telescope is working alone as a single dish telescope. It's working alone, taking a data working alone.
If you have it connected to your room.
Yes, not if you have it connected, but that's not the right way to use if you have it connected. If it works as a single dish, then your back end is the root. That's the best.
If it's nothing.
It's called the VLBI.
Okay,
The VLBI mode. Then that back end is the DDBC, or the digital baseband converter.
DDBC.
Yeah, it's here.
Okay.
And then you can see that this is from the European VLBI network. So that's this telescope works in that VLBI array. The Europeans, and then the one in South Africa, there's an EVM. It's called the EVM. So when we are running in VLBI mode, we use this one for our digital analog conversion. And then this data gets recorded on this one, and then this should have this data part should be for this one.
Can you repeat that? You say?
This single dish works in this PC, and then it records its data on this one. Then the DDBC, which is VLBI mode operation, I've got the data on this system. Then, so that's for single dish ELBI. Then we also look at pulses within nested. For pulses, this is the pulsar timer or the pulsar tracking. So this is what's record the pulsar data. It's called PD. It's this is working in partnership with the University of Manchester, so they provide us for observing pulsars. Down here is just a UPS that is powering everything in this one. If there are no questions, then I move to.
No, it's out to asking the LCP and RCP, they work simultaneously.
Yes, it works simultaneously, but they are not the same. But when you look from the power, you see that there's some slight differences between them.
Okay, so in every measurement, you have one of both.
You have both.
Okay.
And you can decide to work with one or you can decide to throw
okay.
away, but mostly we combine the two. For especially for methanol measures, that's kind of good. Any question? Okay, before I come to this place. Yeah, so what I've just shown you the last stage of the data. So from the sky, reflection, sub-reflector, waveguide, through your feed horn, receiver, final stage of the receiver, gets digitized, recorded data, this analysis, recorded data, then from there you can give it to the crazy astronomers, whatever they want to do, if they do it. So now I just want to show you the other supporting systems that helps you to do. So let's move to the second one. Okay, so from here we have the main PC that runs the telescope, or that runs the drive system that I talked to you about, the servos and all that. So that PC is called the station control system, I think so. And there are two of them, one and two. They are just serving as backups, though all of them are running at the same time. So if anything goes wrong with this one, we switch to this one. If anything goes something with the two, we hang on again. No, you don't need to scratch. It's just
He wants to see.
you don't need to scratch. Maybe just
Yeah, he must watch.
okay. Yeah, so from here, this contains the main operating system that a telescope uses. And that operating system is called the field system.
It's called the what?
The field system. The field system is developed by NASA when they were doing deep space tracking in the 1970s. And since then, that software has been used by astronomers to control telescopes around the world.
So that this automatically switch over the minute.
Yeah, they are all supposed to be working all the time. So if the power goes off and it comes back on, it should come back by itself. And it's just a high-end computer. It looks like a normal PC, but it's just high-end. So you have many cores, many processors, and you should be able to work very fast to do what you need to do. This HP Pro and so we have the Dell.
How much money do you? Yeah, how big is it?
I don't know, but I'm sure it should be at least 32 gig of memory.
22.
Yes, at least 32. And then maybe Password 512 or 128. I don't know. Maybe I could check. Okay, so that's on this one. Yes, there's a question.
Does he run online? Do you need internet?
Yes, you need internet to run, but you cannot get out. You cannot get through from outside without access. You have secure firewalls that if you don't know our IP, you cannot. And even if you know our IP, you just can't do that. You need to have special configuration.
How often do you do observations here?
I don't know.
Like say maybe in a week?
Now that we're here, I've been working consistently for the past 4 weeks.
Okay.
Oh, it's
Even just the Friday I did observation.
okay. How many, approximately how many, the average?
It depends on you, time, the sources you want to observe, and how long you want to observe it, and the conditions.
Well,
So, average, I don't know.
Like the even maybe you have 3 consecutive days running?
Yes, you
72
could.
hours?
You can.
Oh, okay.
You can. But that's what I say. It depends on you if you're not tired.
Oh.
If you give me 1 week, I can sit here 1 week and observe, but it has to be in the night. I want to be with my wife and children. So I will not want to be here every day. It gets really cold here. Yes. But I wish I could, because I have some sources I want to observe alongside your observation. The last week when they were here, we started observing. They came in around 10 o'clock, but I was here from about 8 o'clock in the evening, and we closed around 2 a.m. We observed only 5 sources.
How long is the run?
Is that?
How long is the run?
It also depends again on your science.
oh,
So you could observe a source for 1 minute.
Oh,
Yes.
for one?
1 minute.
Oh, 1 minute.
And you
No,
could
like
observe
the
a source for
maximum.
30 seconds.
The
You
maximum.
could observe a source for 30 minutes. You could observe a source for 1 hour. So on
Oh,
Friday we
okay,
observe a
so-
pulsar for 1 hour continuously. So if you want to observe 5 sources, you need to take 1 hour. Somebody has to be here for 5 hours. That is if nothing goes right. So that means he goes 5 hours non-stop. If something goes wrong, he could go 6 hours, he goes 7 hours, trying to fix what was the problem and continue what he needs to do. Yeah. So
Now I'm just sort of comparing to what we have at home. Like that one is the memory
yes.
radiation test. So it's like the maximum observation per run is like 28 minutes.
28 minutes.
Yeah.
Okay. For this one, for radio, that's why I say it depends on the resources and what's available. Some observatories will not observe anything beyond 25 minutes or 28 minutes because of resources. So like, no, we can't go beyond that because maybe there are a lot of kids we have to go observe them. So like, we are strict. So for like right on the DNA, I use the DNA, the one in the US before. Each observing session is 28 minutes or 22 minutes, 28 minutes, including overhead, including calibrators and all that.
Yes, yeah.
So you don't go beyond that. So 28 minutes, 28 minutes. So if you're the one observing, you have to make sure that everything factors in between it. So sometimes you have that 28 minutes, but the source was observed for only 5 minutes. The real target was 5 minutes. Calibrators are taking the rest of the time. Slowing from one point. Sometimes you could want to move from a source to where you park the telescope to the source can take you like 40 minutes.
Yeah.
20 can take you 40 minutes. Yes, 40. Depends on where you are parked, the previous day or the previous time.
What's the speed? The
Speed is I think 0.05 degrees per second.
0.5 degrees per second.
Yeah, I think 0.05 degrees per second.
Or 0.05.
0.0.
degrees per second.
So if you're tracking for long, it takes a lot of time. So that's on the station controller. Then this one is called tongue, and tongue is powering the infrastructure controller. That's the front end. And then as usual, this rack, this UPS is powering all that is in this rack. And then over here we have the clock or the standard to tell you your accurate time that you're observing. And then it's sitting on a GPS that is outside on a mast somewhere. Maybe if you have the right tool, will show you. So this gives us the time. So this GPS that are locked onto some satellites to tell us write time and date and time. Later within this year, we'll stop using this and we'll now have a hydrogen user that will be producing something
Oh.
outside.
That's interesting.
Yes, sir. Okay, any questions?
You said the tongue, it's a part instructor for what?
What?
The tongue.
The tongue.
Yeah.
It's the PC that's controlling. It's called infrastructure piece. Just something like that. It gives it's working in tandem with this one.